In video number 46, we discussed the importance of voltmeter impedance. In contrast to digital voltmeters, which often have DC input resistances in the range of 8 to 10 megaohms, and vacuum tube voltmeters, which are commonly in the range of 10 to 11 megaohms, VOMs have much lower impedances, and they're specific to the voltage range being measured. In this video, we look at a recent find, an RCA Institutes VOM, which was a kit assembled by people taking the RCA radio and TV courses in the 1950s and 60s. This particular meter cost me $7, and it was in very poor shape when I got it. I got it because I don't have a 20 kiloohm per volt meter on my bench, and this seemed like a low-cost candidate for restoration. Let's get started. This is the schematic I found. Note how clean and simple the circuit is. There's an input here, and current follows a resistive chain that then leads up and into a meter. This is a 50 microamp full-scale deflection meter, and then follows, in the case of DC, back to the common input jack. There's a capacitively coupled output jack here that will pass any AC component of a DC signal coming in. And so that's a very nice thing whereby you could study ripple on top of a DC output, for example. Now, I wanted to spend a little bit of time going through the DC input to such a meter because I think it's representative of other higher quality meters, and it's a way of understanding both input impedance and meter sensitivity at the same time. Let me zoom in just a little bit here so that we have a better picture of the values. So consider a positive voltage being applied to the positive input jack of the meter. And if the meter is set to the highest voltage setting, in this case 500 volts DC, then that switch is going to bring the voltage to here. It's going to see an 8 megaohm resistor and a 1.5 megaohm resistor. So we're up to what, 8, 9.5, and then a 400K resistor. So we're at 9.9 megaohms so far. And it's going to flow through an 8.1 kiloohm resistor and a 17.9 kiloohm resistor before coming into the ammeter. And then once it goes through there, it doesn't see any more resistors on the path back to common. So if you add these up, we have 8, 9.5, 9.9 megaohms, and then we take this 80.1K and the 17.9K, and that sums up to be what, 9.998 megaohms, and that is very close to 10 megaohms. And in fact, what we have neglected here is the resistance of the meter itself. So if we assume for a minute that the resistance of this meter is 2 kiloohms, then we have a total input impedance on the 500 volt scale of 10 megohms. Now I'll just simply say that one can measure this, but generally meters of this sort have meter resistances on the order of a few hundred ohms to a few kiloohms. So approximating this as 2 kiloohms without measuring it is not an unreasonable thing to do. So what? So we have 10 megaohm input impedance on the 500 volt scale. Well, how do we understand that with respect to the 50 microamp meter? Why did they pick a 50 microamp meter? Well, they picked a 50 microamp meter to be 50 microamps at full scale deflection. If you take 500 volts in and you divide that by the total resistance in the circuit, which is 10 megohms, then you get 50 microamps. So at the highest voltage on the scale with this resistance, you end up with full scale deflection. And you can see that if you put 600 volts in or 1,000 volts in at 10 mega ohms, that's not enough to limit the current through the circuit, and you will get more than 50 microamps through the meter, and you will damage the meter. But then how do we understand that for the next highest scale, which drops 8 mega ohms out of the circuit? How did we get 100 volts DC? Well, again, just applying Ohm's law here. If we have 100 volts going through the remaining 2 mega ohms of the circuit, right, because we are bypassing that 8 mega ohm resistor, then we end up again with 50 microamps current at 100 volts. So you can see that that's the highest voltage you can read on that scale without damaging the meter. If you have more than 100 volts, then you need to go up to the 500 volt scale. And you can just do this on down through the resistive tree in the DC circuit. The 25 volt range, there's only 500K of resistance remaining in the circuit, and that is what limits the current to 50 microamps. And you can do this, just as I said, so on and so forth, down through the various voltage ranges. Well, a really easy way to summarize this is in terms of the meter sensitivity, which again we talked about in the previous video. And so you can find what the input resistance or the input impedance is for any range just simply by multiplying the voltage range by the input sensitivity, which is specified for the VOM itself. In the case of this meter, it's 20 kilo ohms per volt. So 500 volts times 20K ohm per volt gives 10 mega ohms. On the 100 volt scale, we have 100 times 20K, which gives 2 mega ohms. On the 25 volt scale, we have 25 volts times 20K, or 500 kilo ohms, and again, so on and so forth. So there's nothing particularly complicated or complex about these calculations. They're just simple examples of Ohm's law. But I thought it would be good to go through that just to shed a little bit of light on not only meter sensitivities and input impedance, but to show how you could, in principle, design your own voltmeter given a milliammeter that you have and set of resistors. Well, so let's look at the meter itself here. I just want this to be a short video on this find. So here we go. As I said, this was part of a kit from a radio and TV course, which was potentially mail order. And, so it's a RCA Institutes. Here we can see the input impedance on DC quoted. Zoom in just a little bit here. Quoted as 20 kilo ohm per volt on DC and 6.67 ohms per volt on AC. This wasn't clean and shiny when it came. I had to disassemble all of it. And there's Apollo the radio dog barking in the background. I had to disassemble all of this and clean it up and polish it up, and it turned out quite nicely. It's shiny and clean-ish. It's certainly clean enough for my bench. So just a couple of things to say about it. First of all, it did not have these banana plug inputs when I got it. It had the old-time, what I will call needle connectors. I don't know what they're actually called, but this was one end of the plug instead of a banana plug. That was this needle, and it inserted into the plug like that. And it's very loose now. It was probably loose then. It's just a horrible way to make a connection. So I took those off, and even though it came with leads, no way on earth I will ever use those leads. I took those off and put banana plugs on them instead. These are very inexpensive, very frankly cheap plugs, but you know, they'll do the job for a piece of gear which I will use fairly rarely. Okay, so there's that. Let's see, well, a couple other things I just wanted to touch on. Let's go back to the schematic. And one thing that you will, if you study this, you will not see a fuse. And this just boggles my mind why RCA, of all people, would teach people electronics without having a fuse in a piece of test gear like a VOM. But you know, if you look at schematics of the Simpson or the triplet VOM meters, you will see input protection. You'll see fuses, which are typically on this leg of the circuit, and that would be, you know, very easy to put in to this meter. But so I wanted to point that out. Other thing I wanted to point out is the for the resistance measurements, for the resistance part of the circuit, it requires batteries. It requires a 1.5 volt battery, which is no problem, and it requires a 6 volt cell, which I think is a problem. I am not real up on my battery histories, but I suspect this was a 6 volt battery that was probably made in the 50s and 60s that no longer is in production. Now, that said, it would be very easy to put 4 smaller 1.5 volt cells in here to get 6 volts. You know, just put in series 4 AAA batteries. There'd be more than enough room to mount a holder in this case. I opted not to do that. And in fact, I opted just to simply take these out of the circuit. These were both corroded almost beyond recognition. And I did that with the rationale of I will never ever use this to, or will want to ever use this to actually measure resistances in a circuit when I've got digital multimeters coming out of my ears. So in this particular instrument, the resistance function is not working, and again, I did that on purpose. All right, that just about covers it. Now let's see how this performs. I won't open this up and show you the inside. It's very boring, as you might expect from the schematic. Let's set up some voltage tests and see how it came out. So these are the leads that I'm using. These came off of an old Radio Shack meter that I had purchased in the 1980s, and they'll do just fine, thank you very much. These actually are rated at, well, the wire anyway, up to 2,000 volts, which this, you would need your head examined to use this to measure 1,500 volts AC with. But that said, these leads will do just fine, thank you very much. All right, so let's plug in our power supply here. We're going to set this first on 5 volts and try to get both of these in the shot and make this a little bit larger and try to get rid of the parallax there. It's not too bad. All right, so the first thing that I want to do here is make sure that our meter is mechanically zeroed, and it's not too bad. Okay, let's make this 0 volts. Turn the output on. Okay, now let's bring this up to 1 volt. This is on the 5 volt scale. Let's bring that up to 1 volt and look at that. It's just dead on 1 volt. Let's bring it up to 2. There we are at 2, 3, a little bit off at 3, 4, and 5. So not too bad. Again, I didn't replace the resistors up here, which are not an issue for the 5 volt scale, right? The only resistor that's an issue here is the 80.1K and again the 17.9K resistor. And those are frankly oddball resistors to come by. And so my substitutions were not quite exact there. But this is certainly tolerable, and I don't know, because I don't have a manual, what the stated accuracy of this is. But at 5 volts here, let's see, look at this a little bit closer, we're reading 4.85 volts. So that's almost certainly within spec of what you could expect this instrument to be to begin with. So now let's go up to the 25 volt scale, and we should be reading 5 volts, and you see that we're just bang on 5 volts on the 25 volt scale. So let's now go up to 10 volts. There's 10, bang on. Let's go to 15. There's 15, and you see that we're again right on 15 volts. Let's go up to 20. There's 20, and we're falling just a little shy of 20 there. And 25 volts, there we go. At 25 volts, we're just a hair off there as well. So here we are on now the 100 volt scale. And let me just zoom in on this much closer, right? And just so that we get rid of any parallax that we could possibly have. So what are we reading here? Well, midway between 20 and 40 is 30 volts, and we're midway between 20 and 30. So we're reading 25 volts bang on here. Okay. Now, my power supply goes out at 32 volts. Okay. But I think you can see that we're reading 32 volts here on this scale. So let me now kill the power and go to series mode on my power supply. Okay. And so now I'm going to have 20 volts out. And so there we are at 20. Okay, 22. 24, 26, okay, so on and so. So there's 30 volts, and I'm just going to dial this up now. Okay, so there's 64 volts, which is as high as my supply will go, and you see that we're reading 60 volts, so a little bit out there. If we go up to the 500 volt scale now, what does that mean? Well, 500 volts would be the 5 volt scale multiplied by 100. Okay, so that would be 100, that would be 50, so 60, and you see we're just a hair over 60 volts there. And so that would be entirely believable that it would be 64 volts. All right. So I'm pretty happy with how this performs on DC. We can ask a similar question about how it behaves on AC. And let me set that up, and we'll be right back. All right, so I've got the Tektronix set to measure volts AC, and just want to set the RCA to the AC scale. And the first thing that I'm going to do now is set this to the 25 volt. I'm sorry, the 75, let's go to 15 first. 15 volts AC scale. And over here I've got a BK 1653 isolated variable power supply. The fact that it's isolated is not important for this video. The fact that it's variable, it's essentially a variac, but it's not as far as we're concerned here. So I've got this set down to 0. I'm going to turn it on and just bring up the power, the voltage, okay? And so there we're just essentially at 6 volts AC. You can see that we're on the, now it's the red scale down here now, 6 volts AC. Bring it up a little bit more. Okay, so there we are at 12, and we're a little over 12 on the DMM. Now let's bring it full scale here. So my supply is a little touchy, but there's full scale 15 volts, and we're reading, what, 15.3 to 4. Okay, now let's set this now to the next higher scale, which is 75 volts AC. And you can see that on here we're a little over 15 volts, and on here we're just a hair over 15 volts. Now let's bring this up now, and let's get close to 45. There we are. You see that we're 45 volts on the RCA, and we're at 44.2 on the Tektronix. We can go up more. So there's neighborhood of 60, and then 75, and we're very close there. Okay, and we might as well just go up now to the 300 volt scale and bring the auto transformer farther up. So there's 120 volts on the RCA, and we're at just shy of 121 on the Tektronix, and I can bring this up to close to 140 volts. Let's just stop at 140. Okay, and you can see here that we're right at 140. So not too bad, not too bad at all. If I was a bit more careful with my choice of resistors, we could increase the accuracy here, but not too bad for an afternoon spent adding resistors in series and parallel, and trying to make this a one-day project. All right, one last thing to do is to look at the current performance in this. Let me set that up, and we'll be right back. All right, we've got our little DMM checker, which we've seen in previous videos. This is a very nice piece of equipment to have on the bench for these sorts of occasions. And what I'm going to do now, this is a standard output of 5 volts DC and 1 milliamp DC. So I'm going to now just change this around to the 10 milliamp scale and see what we get here when we look at the current. And we have no response because it's still on the AC mode. So when I change it to DC, we get deflection. And if we zoom in on this, we see now that on the 10 milliamp scale, so how on earth are we to read this? Well, 100 up here on the DC scale will equal 10. So we're going to have to divide, right, because we're on the 10 milliamp switch down here, right? This is 10 milliamps. So full scale deflection on this range will be 10 milliamps, not 100. Okay, so let's now zoom back in. So we're going to divide everything on the 100 scale by 10. So this would be 10 milliamps. This would be 8, 6, 4, 2. So this would be 1 right here. And let's go back now to our 1 milliamp source and see where we are. If I can get the needles there. And look at that. We're right at 1 milliamp. So it seems to work, and it seems to work quite nicely. Don't want to make this longer than it needs to be, but here is a 20 kilo ohm per volt meter that cost a grand total of $7, plus a little bit of change in terms of resistors that I had in stock and changing out the jacks for banana plugs. RCA Institutes meter assembly kit. Turned out pretty nicely. I hope you found this interesting. If so, please give a thumbs up below. And as always, thanks for watching.